What's up, scholars? This is our first set of notes on our new unit, momentum, impulse, and collisions. So in order to talk about momentum, as we've already gone through, we're going to be talking about things colliding usually just in one dimension and with two objects. So what's important to note is when we talk about collisions, there's always going to be the information before a collision, and there's always going to be information after a collision. So let's just say maybe we'll start with two objects, mass 1 and another object, mass 2. I've not intentionally drawn them to be the same size or the same mass or anything like that. This can be pretty darn generic. And what we'll say is that both of them have some generic velocity. I'm going to put a vector hat on top, and I'm going to put v1 subscript. So this is the velocity of mass 1 before the collision. That's what the subscript naught is there. And then v2 naught will be the initial velocity before the collision for the second object. Now, a lot of what happens will depend on the various things, like how big is the mass, what's the velocity, and so on. But after the collision, you'll have something similar. So you'll have m1, you'll have some final velocity of the first object, and m2, some final velocity of the second object. Now I use the term collision very loosely here, as we'll see. This also applies for explosions, for rockets, for all kinds of things. The next thing we want to address is something that's very important in physics. It is one of the more fundamental conservation laws, the conservation of momentum. So here is the law of conservation of momentum. If you need to pause and write down the definition, you can. I'll read it. The total momentum of a system remains constant or unchanged during a collision, and this is a consequence of Newton's third law. Now, some people might argue that, in fact, the law of conservation of momentum is the fundamental thing, and Newton's third law is the force consequence of it. We can disagree and argue about that. The definition of momentum is very simple. The momentum p, which is a vector quantity, is just the product of mass times velocity. The units for momentum are just found by taking the unit for mass times the unit for velocity, and it's just kilograms meters per second. There's no special name for it like Newton or Joule or anything like that. And really the reason for that is because we very rarely actually want to know the total momentum something has. Instead, we want to know, as I showed up here, its velocity or its mass or something along those lines. So a common practice in physics is taking old stuff and rewriting it when we learn new information. So we're going to take Newton's second law and we're going to rewrite it including momentum. It's pretty easy to do. The acceleration is defined as the change in velocity over time. Now, notice I am trying to use the vector hats wherever I can. I'm going to try to be careful and do that throughout this unit. So we'll insert the definition of acceleration, change in velocity over a change in time. And then we'll simply we can rewrite this in a particular. Now, often when we're talking about collisions and stuff, the only thing that's going to change is going to be the velocity. Technically speaking, conservation of momentum and Newton's second law apply even if the mass changes. So what we're going to do is we're going to pull the delta for change out front, and we'll pull the mass inside. So technically, that entire quantity, mass times velocity, can change over delta t. And then you'll notice there we've got m times v. So F net is equal to the change in momentum of an object over the change in time. That is just Newton's second law written with momentum. If you're in calculus, you can say Newton's second law is the time rate of change of momentum with respect to time, or the derivative of momentum with respect to time. Something also worth taking a look at is rewriting the kinetic energy equation using momentum. This is a practice often done in particle physics and some other areas of physics, but it's good practice, and you may see this show up here and there. So let's do that. That's just going to be, well, we want to see if we can get mv in there somewhere. So let's rewrite this as 1/2 times m times v again. Look, right there is our momentum. So I'm just rewriting it in kind of a funny way. Continuing with our rewriting it in a funny way, I'm also going to just multiply and divide by m. I'm sort of adding extra information. You'll see why in just a moment. So I'm going to both multiply and divide by m. The reason we're going to do this is you see now I have mv and mv again. That's momentum twice. So that's just 1/2 times p and p, so momentum and momentum again. So p squared over m. So you can rewrite kinetic energy like this, p squared over 2m. And the reason we might do that is, again, for particles. A lot of times when people do particle physics research, it's much easier to know the momentum of a particle than it is to know its velocity. So we've covered the basics with momentum and how it relates to some things we're familiar with. Now what we're going to do is derive the conservation of linear momentum equation. So we're going to play around quite a bit with this simulation since we're not able to do experiments in class, though we will look at some real data from some real collision carts that we have in the classroom. Anyway, meanwhile, we can look at just a generic type of collision here. These two objects are going to hit and bounce off of one another. So this is the information the moment before. I've just kind of randomly moved this around. And this is something we may not use actually in class, but it's a helpful thing to see here, which is a momenta diagram. So you can see object 1 has some momenta going to the right. Object 2 has some momenta going to the left. Notice they are vectors. And if you add those two vectors together, you end up with a total momentum to the right because this one is heavier and moving faster. Anyway, when I let them collide, what you're going to notice is that the total amount of momentum to the right remains unchanged even though they've collided. So check this out. They're going to bounce off of one another, and the total momentum, even though the velocities changed, the total momentum stayed exactly the same. Now, that's true there in the case where the two bounced and moved apart. That's called an elastic collision. We're going to talk more about that. It's also true for an inelastic collision where they hit and stick together. We can see here the momentum again starts out being to the right and it ends that way after they hit and stick. The total momentum remains unchanged. That's simply the definition of conservation of momentum. There you go. Take a moment, draw this situation. We've got the moment before and after a collision with our two masses. Keep in mind, this technically will work for any number of masses, and they don't have to be moving towards each other. They could both be moving in the same direction or any combination of that. Something that we already know is that when objects collide or interact in any way, they exert an equal and opposite force on one another. So what we're going to do is we're going to use both Newton's second and third law to derive this thing. So what we mean is that we're going to have the first object, the force on it is going to be equal and opposite the force on the second object. I'm going to annotate those real fast. Alright, so this means the force on mass 1 from mass 2, and this is the equal and opposite force on mass 2 from mass 1. To do this, we want to remind ourselves both of the definition of force in terms of momentum, the change in momentum over the change in time, and that the definition of momentum is just mass times velocity. So what we're going to do is replace these forces with the Newton's second law definition here. So I've used Newton's third law to set up the equal and opposite forces, and then I've used Newton's second law, rewritten with momentum, to sub these in. Now, the change in momentum is going to be, again, equal and opposite, but we can cancel out the delta t's there because the amount of time both objects experience during the collision is going to be the same. So what we're left with is that the change in momentum of object 1 is equal and opposite to the change in momentum, or of the object momentum 2. So for this derivation, which actually isn't too bad, I'm going to write each line, pause, and then explain each line. You're welcome to pause and write down that line as well. So I've simply replaced the momentum of the first object with its definition, its mass times its velocity, and likewise with the second now. I've added this little note here just to remind us that delta means the change in anything, so to kind of expand that out, we just take the final quantity minus the initial quantity. In this case, what we're going to assume is that the masses are going to stay the same. We're going to assume that that's true for all the collisions that we talk about in this. If you get into things like rocketry, it can get a little bit more complicated where you're spitting mass out the back of your rocket, rather, and we'll talk more about that. So I've expanded this out. The final quantity here that we're talking about for the change is going to be the final momentum of mass 1. That's just its mass times its final velocity minus the mass times its initial velocity. We can fill in the other side as well. So I've also expanded this out. I won't write those in. You're welcome to do that as well. Important, we've got to keep our negative sign out front. The next thing I'm going to do is simply distribute that negative sign into this and then rearrange. So I'm going to do a couple of algebra steps at once to save a little bit of space on my paper. See if you can follow along. Again, I'm going to distribute the negative sign and then flip everything around. So see if you can convince yourself that I did that correctly. I distribute the negative side, so this is negative. I added it over to this side. This term becomes positive, and I add this over to here so that they're joined up. So I've got the final quantities and the initial quantities. Now, we normally think in the English-speaking world left to right, so I'm just going to flip this equation. As promised, I flipped the sides. We put it in a box so you know it's important. That's our conservation of linear momentum equation. Now, I want to make this seem as simple as possible, so I'm just going to label both sides of this. This is just the total momentum before the collision. See, total momentum before collision. And this over here is just the total momentum after the collision. Oops. So what we mean is that this is just the momentum of the first object, the momentum of the second object. If we had more objects, you'd add the momentum of the third, the momentum of the fourth, and so on. And this is all of that before. However much we had before is going to be exactly equal to whatever we had after. So this equation is going to do a lot of work for us. Because there are 4 terms in it and 8 symbols, there are a lot of different ways we may interact with this equation. Thanks, folks.